So I think we should begin. Welcome everybody to the third of the Angewandte Fall Symposium series, where we are taking the opportunity to introduce our new scientific advisory committee to the chemistry community. The talks of the other 7 members were given in 2 symposia in September and October for the Asia, Oceania, and Europe-Africa time zones. Today now is the 3rd symposium of the series for the Americas time zone. All talks are made available to view via the journal homepage in case you are interested to hear what was spoken in the previous symposia. After this short introduction, then 3 members of the Scientific Advisory Committee will give a talk about their recent research as announced. Will be 25 minutes each. We ask you to use the Q&A function to ask scientific questions to the speakers. After each talk, we have about 5 minutes for scientific questions. And after the last speaker, we have 30 minutes for a Meet the Editor session, where you can ask questions to the advisory editors or to the 2 members of the editorial team who are moderating the symposium. That is Suzanne, Tobey, and myself. So many of you know and have published or read articles in Angewandte Chemie. But what may have passed you by is the fact that Angewandte Chemie is owned by the German Chemical Society, or GDCh for short. So it's a society journal. The German Chemical Society is based in Frankfurt and has around 30,000 members. The GDCh plays an important role in the worldwide chemistry community, but it also plays a role in the development of Angewandte Chemie. Shown here is an overview of the new governance structure of the journal, just to give you an idea of how all that works and how we all work together. So on the left is the editorial office, including the executive committee. We are full-time editors, and we work together with the GDCh through the Angewandte Council, whose representatives are shown on the right, including the president, the executive director, the publishing advisor from the GDCh board, and the chair of the International Advisory Board. The Scientific Advisory Committee is a group of 10 scientists with excellent scientific background in all different areas, and they cover all different fields of chemistry. The advisory editors help us in identifying areas for needed change and in developing ideas on how to move the journal forward. They support the in-house editors in their decision-making process, particularly for the more difficult decisions that we have to make from time to time. They bring their experience, so to say, from the bench in the decision-making process at the journal. Similarly, the International Advisory Board covers all different areas of research, and their members come from all different countries and backgrounds, and they help not only with the decision-making processes, but also by providing us with important feedback on key developments from their various communities. For Angewandte, it is an honor to have such a fantastic group of chemists and board members who act as ambassadors and role models for the journal. It is also great for us that so many of them are also regular contributors and send us some of their most innovative research. With this said, I would like to move forward to the scientific part and introduce our first speaker, Professor Leticia González from the University of Vienna. Stop sharing for a moment. Leticia studied chemistry and obtained her PhD at the Universidad Autónoma de Madrid. She then moved to the Free University of Berlin, where she obtained her habilitation. She was appointed professor at the University of Jena and full professor at the University of Vienna in 2011. Her research includes modeling of photophysical, chemical, and biological processes. She's interested in light-driven processes on biomolecules, DNA, and coordination compounds with diverse applications ranging from solar fuels to medicine. And in her talk today, she will show us how to simulate the dynamics of photo-induced reactions. And please, Leticia, the screen is yours.
Thank you very much, Frank, for this kind introduction, and thank you to all of you for being there. And it's really for me a pleasure to be part of this this mini symposium and to be part of also of Angewandte. And I indeed would like to tell you a little bit about the work that we do, which is related with light. And light is, let me just put my pointer. Okay. Okay, here it is. So light is basically everywhere in our planet, and given its omnipresence, maybe we don't realize how important it is, but without light, the life that we know would not be possible. So there are many processes that they take place mediated by light. So probably you know many of the examples which are here, like photosynthesis, we see by virtue of light. The fact that we sleep during the night and then we are awake during the day is also regulated by light. You know, the beautiful phenomena of phototropism and many others. And our research is, of course, not so extensive, it's more modest. Basically, we want to understand a lot of the basic fundamental processes that occur when molecules are interacting with light. And this can go from very simple molecules like small, medium-sized dyes, and to larger molecules, like Frank was saying, like, for example, DNA building blocks, which are related to photostability and photo damage in DNA, or larger PCs. We have also been very much interested lately in coordination compounds, and we also have some fields which are like more fancy applications, like how you can just describe molecules that can be applied for making molecular switches or molecular machines, for applications in photodynamical therapy, or for imaging neuroreceptors, or just to try to get an artificial photosynthesis. Many of the commonalities behind these different systems or applications are the following questions. I mean, as a theoretician, you would like to know what happens really to the molecules after you have the light absorption. So what type of electronic excited states are created, how the molecules, the nuclei are going to move. And this is very often connected with how light is going to be able to induce the functionality, like sometimes you also have in nature, and you would like to model it for different applications. So this is related, like how nature machinery can be transferred to technology. Of course, theoreticians, they like very much to treat systems in gas phase, but the exciting chemistry takes place in the environment. And then we also have to face the question how the environment changes different properties. Actually, light can be even used to create new molecules, or one can even use light to manipulate chemistry with a well-defined light. So if I would just pose the question how we can study excited processes, I cannot resist to show the commercial of this book. So this is a Wiley event, and therefore I would just like to show this book that appeared this year, edited with a very dear friend of myself, Roland Lind. And here, basically, we describe all the different methods that many people have contributed during the last decades for studying the quantum chemistry and reaction dynamics of electronic excited states. So basically, when you have excited state processes, you have to make use of two different, let's say, global fields in theoretical and computational chemistry. One could be described by quantum chemistry, which in very simple terms means to solve the time independent Schrödinger equation. And the other is just to solve the time-dependent Schrödinger equation, which can be globally understood as non-adiabatic dynamics. And there is a lot of methods in electronic structure theory. And here I have some acronyms that don't matter at this stage. The idea is that if you are able to solve this equation in an approximate way, you should be able to get energies and molecular properties, but also the topology of the potential energy surfaces that they are going to be involved when you excite the system. And when you have electronic excited states, you have many different potential energy surfaces that they cross among themselves. So you also have to find a way to locate these crossing points and also to get some idea of estimating how large are these couplings to know if these crossings are favorable or not. So when you take any of these methods and then get any of these properties, you maybe are able to put forward some mechanism of how the electronic excited states and how the reaction is happening in the electronic excited state. But it's not until you really solve the time-dependent Schrödinger equation that you can get a sort of a movie of how the nuclei are moving. And this provides you the system time evolution, and then for free also would give you some information about time scales. And if you're lucky, you also might get some information about the branching ratios and the quantum yields, but for sure you also will get a definite answer, which are the defined products that are happening in a reaction. So I don't want to make much emphasis here about the electronic structure methods. I think many people are familiar that there are many different methods with different accuracies, limitations, and strengths. I would prefer here to go into something which is, in principle, a more complicated problem, the idea of how to do adiabatic dynamics. And here again, there are many different methods, but I would just like to explain like two streams which can be achieved or can be considered for solving this problem. So you really take the time-dependent Schrodinger equation and you solve it. This is what is in the theory known as quantum dynamics. And the idea is that you will just calculate potential energy surfaces. So here I have a cartoon with two surfaces or with two potentials, and they also come close here in a point which is going to be reminiscent of a crossing point. So you would excite the system, you would create a wave packet in the electronic excited state, and this wave packet would evolve in time. And then when it arrives to this crossing point, it will bifurcate and give you a branching between two possible relaxation pathways or two different products. So if you are able to do that, to propagate these wave packets, of course, the advantage of this method is it contains all the different quantum effects. But the big disadvantage is that you need to pre-calculate these potential energy curves in advance. So this is a very simple example with one coordinate, but now you have a molecule that has 3n-6 degrees of freedom. You would have to calculate in advance these 3n-6 potential energy surfaces, 3n-6 dimensions of the potential energy surfaces, which is an extremely demanding problem, if not impossible. So the people working in this field, basically, they would just work with model potentials, like maybe harmonic oscillators. And also very often, unless the system is very small, you would have to reduce the system to very few dimensions. There are techniques like, for example, this multi-configurational time-dependent hat-tree, which allow you in a more clever way to extend the number of degrees of freedom. But in general, the disadvantage of this sort of approach is that you work in reduced dimensionality or with model potentials or both at the same time. So the other stream to solve the problem is just to consider a semi-classical picture, in a sense that now the nuclei are going to be not quantum objects, but classical balls. Okay, I have here this ball pointing here. So now these balls, they can be propagated using nuclear, using the Newton equations, so in a sort of like trajectory. And because I have a ball, when this ball is propagated and is arriving to this crossing point, the ball cannot split. So the ball can stay in the upper potential or can hop to the lower potential. This is what gives the name of the surface hopping to the method. But if I want to mimic this behavior of this branching of the wave packet, I need to have a lot of balls, a lot of trajectories that I have to propagate. And then some of them will just stay, some of them will hop, and this distribution will just mimic and resemble this wave packet bifurcating. Now, in this case, the big advantage, I mean, I have the disadvantage that I have classical nuclei, but the big advantage is that I don't need to pre-calculate the potential energy surfaces along all the different dimensions, but I can calculate for the points that I'm propagated, I can calculate on the fly my potentials and get all the electronic structure information that I need. So this means that in principle, I can get ab initio potentials, and I have dynamics in full dimensionality because my ball is exploring as it needs all the 3n-6 classical space. So this is a method that was sort of put forward by Tully already almost 30 years ago and has been extremely popular. And 10 years ago, we just decided to implement our own flavor of this. And this is just called SHARC, which is basically stands for surface hopping, including arbitrary couplings. And the idea is that the standard approach of surface hopping was only including non-adiabatic couplings. So it means that you can only describe crossings or hops between surfaces of the same multiplicity. And there are many cases where you need to have also spin-orbit couplings or other type of couplings. For example, if you want to describe intersystem crossings or crossing between two different multiplicities, potential surfaces of different multiplicities. So we extended this surface hopping approach in order to be able to be more general. So this is a program which is in a GitHub repository, is open source, and if you want to use it, you are certainly very much welcome to do that. And what I would like to do in the rest of my talk is just to show you some showcases that illustrate how you can deal with dynamics in particular systems. And I have chosen transition metal complexes because I believe that they are quite challenging for several reasons. So many of the most of the systems that probably are interesting from the experimental point of view are quite large. So this means that you have many degrees of freedom, and this means the calculation is quite expensive. So theoreticians in general don't like to deal with coordination chemistry. Now, when you have metals, transition metals, you also have a lot of pseudo-degenerate electronic states which are involved, and you need to find electronic structure method that is able to deal with the spans and also the accuracy of describing all the different types of wave functions that you can have, the states that you can have in transition metal complexes. So you also need to have codes that, of course, are able to deliver you non-adiabatic couplings or find a way to recover these non-adiabatic couplings. And you also need to include the spin-orbit couplings. And of course, as I said, if you are not in gas phase, but in environment, you also need to include the solvent effects, which is an additional problem on top of all the rest. So if I would have to summarize some of the challenges, I would say transition metal complexes, they have many electronic excited states of many different characters and many nuclear coordinates. So this is why, in principle, you can only afford to have very short propagations of very small systems, and nevertheless, the calculations, they are very expensive. But I want to show you how we have been able in the last few years to deal with this problem. So here I have this example, this rhenium 3-carbonyl imidazole phenanthroline in water. So this is a complex that we started to study in order to look at electron transfer processing proteins, but we never arrived to the protein stage because we were first just busy with trying to make it work as a proof of concept in water. Now, from the theoretical point of view, when you have such a complex system, I mean, you have this metal complex that I was saying before, where this is challenging for doing dynamics, but you also have it in water. You can exploit this so-called like hybrid approaches, in which you partition your system in two parts. So one would be described with quantum mechanics, that would be the complex in this case. And the rest, all the water molecules, that would be described with molecular mechanics, this means with classical force fields. Okay, so you can, this is sort of like a standard. You can use different ways to do that, like in this case, electrostatic embedding. And then you can calculate an absorption spectrum of the system. And you see in this absorption spectrum, I mean, without going into detail, that you have a lot of these electronic singlet excited states for the region of energy that maybe we want to excite the system, in comparison with, let's say, if there is an experiment with experimental wavelength that has been used for exciting the system. And this is the typical picture one would obtain when you do these propagations of trajectory. So this is average almost 100 trajectories. And you have here a simulation time. So this is 250 femtoseconds, and this is the population of the different states. So we have been propagating 7 singlets and 8 triplets. Remember, triplets are triplet degenerated, so actually you have 31 states, and I have just colored these states here, like all the singlets, they are like bluish, and all the triplets, they are like in these warm orange colors. And you see here, there is a big mess, but basically you see that the singlets, they are decaying very quickly, and the triplets, they are rising also very quickly. So you see that the intersystem crossing is ultra fast. You can collect all the singlets and all the triplets in this way, and then you obtain something which is cleaner, and you have to use a B exponential function to fit this intersystem crossing mechanism, and we obtain like 2 time constants, one which is very fast, it's about 8 femtoseconds, and the other is about 400 femtoseconds, and as a matter of fact, we just assigned this to some electronic intersystem crossing, which means that it's just given, it's just due to the strong spin-orbit coupling that you have there, and the big thick of manifold of electronic excited states. And only after some time, then when the nuclei start moving, then you have also a big time regime in where the intersystem crossing is happening. Now, when you do this type of calculations as a theoretician, you would like to compare with an experiment, and there was an experiment here realized by Tony Blatczek a decade ago. And actually, the experimental time that was assigned to intersystem crossing is something like 140 femtoseconds. And you would say, well, how is this agreement? I mean, this agreement is the same order of magnitude, but it's actually a little bit frustrating, because we figure out that normally with this calculation, you should obtain something which is better. And of course, you have a comparison with experiment and theory. I mean, the experiment is always correct, so the theory has to be, there is something wrong that has to be in the theory, but we could not really find what has to be wrong. And then we just realized, okay, wait a second. So this experimental time constant is something which has been obtained by convoluting, by fitting a time resolved fluorescent up conversion, right? So in the experiment, you always have a first laser pulse that excites the system, but then you have a second pulse, like the probe, which really allows you to obtain a signal, right? Now, when you do these sort of calculations, very often you just stop after the first pulse. I mean, you excite the system, use the dynamics, we get some time constants, and we try to compare them with the experiment. But actually, what one should do is also to simulate the emission spectrum, and this is what we have done here. And then when you fit the spectrum, we just get a time constant of 150 femtoseconds. So this was, of course, very, very nice, because now the agreement is very good. But we have learned that this fitted time constant is actually not the intersystem crossing, because the intersystem crossing was just shown before with the populations that I had a time constant of something like 400 femtoseconds time constant. This 150 femtoseconds is just sort of like an average signal that is just produced by the second pulse, which includes the intersystem crossing, but also includes all the different relaxation processes like internal conversion within the singlet manifold and the triplet manifold. So something which is very important from here is just to remember that if you want to compare with the experiment, you have to simulate the experiment. And this might seem very trivial, but you will just find that, I mean, ourselves for many years, and there's a large community of theoreticians that would just stop after making just the first excitation and then try to compare with the experiment. So this was a very important lesson, that one really has to simulate the same observables if you want to compare with it. Now we see, or I can convince you that these sort of simulations, they can give very accurate description of the experiments. But just as a fun fact, if you want, I mean, these simulations, these propagations, they took almost 1 million co-hours. So this is something very, very expensive, right? If you try to just see, I mean, of course, in a big computer center, 1 million co-hours is just several weeks. But this is, of course, not something that you could just do on a routine basis. So the idea is, or the question is, can we just get a shortcut? And now, if you remember the two extremes that I showed you at the beginning, right? The quantum dynamics versus the ab initio surface hopping. So in the quantum dynamics, you have this disadvantage that very often the people use model potentials. And this looks like a big disadvantage. And however, I mean, it has been very successfully exploited, for example, from the MSTDH community. Now, the ab initio surface hopping also use this is based on this disadvantage that you have this classical nuclei, and nevertheless, it can give you also very nice description of the reality. So why don't we combine, so to speak, like the let's call it the disadvantages of these two methods? And you heard correctly, not the advantages, but disadvantages. And this is what here I just call a linear bibronic coupling surface hopping idea. So this is still based on classical nuclei, but now we are going to propagate this nuclei not on the fly potentials, but on these model potentials, like the community in the MTDH would do. And we still retain the full dimensionality. So you could wonder why on earth you would like to make to pursue this idea to propagate on pre-parameterized model potentials, and the answer is that this would speed your propagations by orders of magnitude. So I'm just gonna spend one slide just telling you, I mean, this linear bibronic coupling model sounds very exotic, but it's just basically a shifted harmonic oscillator approach. So you have a lot of harmonic oscillators, and in the simplest approximation, they are all identical, right? And you are just gonna shift it. I mean, this is just a two electronic case. You're gonna shift it vertically and horizontally, depending of this inter and intra couplings, right? But basically, the only thing you need is just the normal modes of the system, so the frequencies, the excitation energies, and then you calculate these intra and interstate Bernoulli coupling terms, and then you can just set up a model and propagate trajectories on that. So the problem of these is, of course, the basic problem of using harmonic potentials, right? You don't have harmonicities, so it should only be decent and okay if you have rigid structures. Now, when you have transition metal complexes, I mean, this is, I would say, like the perfect case of rigid structures. So of course, this is a model that is only close to the reference geometry, okay, so you could not describe dissociation. That's something that you have to take into account. But you are able to have a full dimensionality case. So it's not like in quantum dynamics that you need to make some decisions about which degrees of freedom you're going to take. You can take all of them. And this basically means that in comparison with on the fly, you can afford higher level of theory, longer propagation times, more states, and more trajectories. And in order to illustrate this, I just want to show you the last example that we have used with LBC. And this is this transition metal here, this vanadium complex. And this is an excited candidate for photoluminescence in the near infrared range, because it's able to emit in this range of 1,100 nanometers. So this makes it very useful for applications in vivo bioimaging. Now, and also, I mean, this has like this abundant 3D metal, so there is a lot of efforts to try to get useful complexes that they don't employ heavy, expensive metals. Now, for theoreticians, this vanadium poses a new challenge, and this is that now we have a D2 configuration, so we have a triplet degenerate ground state. So until now, the example that I show you, and I can just tell you every single thing that we have done until now, it was always starting from a singlet ground state, and you will just excite to singlet electronic excited states, and then from the singlets you would get to the triplets. But now we have intersystem crossing that is from the triplet to the singlet. You would say, well, so what? But I just want to show you in a moment that this is quite challenging from the theoretical point of view, and you have this degenerate ground state. So if you cannot see much in the picture, but I just want to tell you, well, if you just take into account these Tanabe-Sugano diagrams that the inorganic people love to have, you can just really build like all the different electronic excited states that you're going to have in this complex. And then I just want to show you like these ones here, they will not be described by single excitations. These ones here, they will be very badly described by single excitations. And these ones, they are just belonging to this by definition multi-reference ground state. So you cannot use a method like independent DFT. You need to use a method, a multi-configurational method, like the simplest case would be like CASCF. So in this case, we just built the so-called active space. I mean, this is how many orbitals and how many electrons can you take for this, and try to do surface hopping dynamics. Now, if you would like to do surface hopping dynamics on the fly, and let's say that you want to propagate for 1 picosecond and you want to propagate 100 trajectories. If you do it on the fly, you would need something like 50 million core-hours. Okay, so this is something like 1,700 years, right? So this is, I mean, if you try to apply for 50 millions of core-hours in any computer center, they will just probably send you home. So this is a hopeless case. Now, if you try to do an LBC parametrization, I mean, this requires like 250 calculations, and this is nothing like 20,000 CPU hours. And if you just propagate 100 trajectories for 1 picosecond, this costs you 300 CPU hours. So you see 300 CPU hours versus 50 million CPU hours is really a thing. And what you can do is even invest a little bit more and then not just do 100 trajectories as normally the community in the ab initio excited state dynamics would do, but yeah, do like 2,000 and not just do 1 picosecond, but to do 10 picoseconds, and still this would be only like 60,000 CPU hours. I'm just showing here the result of these propagations, and you see here just like the 1 picosecond. And again, I mean, in bluish, we have now the states which are decaying. In this case, they are the triplets, which just go down, and the singlet, which is kind of growing, it's just shown here in this pinky. And after 1 picosecond is something like 10%. So 10% was something bad because we knew that from the experiment they had something like 1% of intersystem crossing the triplet to the singlet. And only when you propagate longer, up to 10 picoseconds, and I blow up here just the population of the singlets here, you see, I mean, after 1 picosecond, you got this 10%. But then this reverse, I mean, this decays back, and you see now there is the growing of this other triplet here is just different. And then it's something like only 2% in 10 picoseconds. So you can take this course and then just fit some kinetic model that in this case is quite complicated. And you see we start with the triplets and you have intersystem crossing to some metal center singlet in something like this 10%. Then you have reverse back intersystem crossing from the singlet to the triplet. And this is what now, I mean, this is like 9%. So at the end, you only have this 2%, which remains after some time. And then basically the rest, this 80% and this other 10%, it's just going to other triplet states. So in total, one can calculate something like 1.6 picoseconds intersystem crossing time, which is in a very nice agreement with the experiment, which is just 1.5. And I mean, I think that, I mean, this is a very recent thing that we have just published together with our experimentalists. You can find here in this back-to-back two publications, the experiment and the theory. And I hope that this shows you, I mean, the power of this LBC surface hopping dynamics. And here I just wanted to summarize what is the computational cost that a surface hopping can take. So this is of course very biased because it refers to the work that my group has done basically in the last 10 years. And I just wanted to plot the cost in CPU hours to propagate for 1 picosecond, and to show you here how many degrees of freedom one can afford, right? So if you take, we have been working a lot in organic photochemistry, so you take molecules like that, which are not very large, maybe you come to like 50 degrees of freedom, the cost will be in the thousands of CPU hours. I mean, this doesn't mean that we have done it, this would be the cost that you would extrapolate to this time. If you use not this sophisticated like CASCF or CASP2 MRCI methods, but something much cheaper like independent DFT or ADT2, you can really go to larger systems like transition metal complexes, like this example that I show you here, or others. But in all cases, you are talking about thousands of hours per picosecond. Now, you do this linear bioimaging coupling method that I was just showing you before. I mean, there are like few examples because we started to do this very recently, but you can see that now we are in like the 1 CPU hour per picosecond. So I think this is very promising, and I would just expect that this should be in the future used more extensively. So I just want to conclude, and I hope that I could show you that surface hopping, and I mean, we have this code, but of course there are more around, but with Carrot you can have the intersystem crossing also described on the same footing as internal conversion is a very useful method. Now this idea of combining surface hopping with linear bioimaging coupling methods allows you to have a very efficient implementation of surface hopping. So one of my students just put here this super chart, which is sort of like a funny, and basically, this allows you to have more trajectories, better potentials, and longer time scales. And in the last example, I hope that I could show you that sometimes it's really important to be able to make longer propagations, because otherwise you would just miss half of the story. Is also just to show to throw some word of caution with open shell systems that very often one needs to go beyond mono-reference methods, and this is extremely hard to do with on-the-fly trajectories. And with this, I really come to the end, and I want to thank all the brilliant people in my group who actually has done the work, where the funding comes from, and the Vienna Scientific Cluster that give us the computer time to do many of these calculations until we started doing LBC. And of course, all of you for your kind attention, and happy to answer any question. Thank you.
Thank you, Leticia, for this great talk. Let me have a look if there are any questions. So not yet. Maybe I have a question. So this QMMM method you have shown, where you separate the active center from the surrounding protein shell. Do you think that with more computer power, this protein shell can be included in the quantum mechanical measurement, or is there a fundamental limit to doing this?
I mean, so the idea is, I mean, you basically partition in two parts, right? And the bottleneck of everything is always the quantum chemistry. I mean, in the quantum chemistry per se, but also the dynamics and everything, right? Because you cannot get away of the quantum chemistry. So if the quantum chemistry gets better, let's say not because of the larger and faster computers, because this is too slow for the growing. I mean, the computers, they double the speed every couple of years, but with this, you cannot double the size of the system, yeah, because the scaling is very large. So there are a lot of groups working on making linear scaling methods, and this allows you to have like larger computations of the quantum mechanical part. So there are examples where it shows that sometimes, I mean, not maybe in this very simple system where you have a molecule and it's in solution, but let's say you have some more complex environments, it might make sense to include part of this environment also in the quantum mechanical region, right? To describe it with quantum chemistry. And then having, okay, let's say like more efficient computers, but I would say more clever methods or more powerful methods on the quantum chemistry allows you to have a larger QM region. I don't think that it makes sense to take like all these thousands and thousands of water molecules into the QM part. Right. I mean, there are also more sophisticated ways of doing this embedding, but I mean, these are like, I would say that there's a reason why this is described classically, because these effects, they're not so important, but it might be. I mean, it depends on the system. Yeah, I mean, so you have more complex environments. You have, for example, DNA. I mean, you might also have chromophores here and there. If you have, for example, in the artificial photosynthesis, you might have soft matter environments that they're also active. Then, of course, it makes sense to have this in the quantum region. And then the more that you can afford for the quantum chemistry, the better. Of course, the computers help, but they don't help at the speed that we would like to have.
So there's a question from Tanya Cordova. Great talk, thank you. Is Shark available for academics?
Yes, so Shark is available. We have a GitHub repository, and everybody can just go there and download the code. So this is totally free of charge, and you only have to use the same sort of license that we have if you want to take it, whatever. So yes, this is free for the academics without any problem.
And one more question is, have you tried semi-empirical methods for the environment portion? So for the
No. So this is something that it might be useful, as I said before, it depends on the type of environment that you have. Then it might be necessary to put them in the QM, and if you cannot, then you can have like different levels of QM, like there are this multi-layer QM1, QM2, MM. So this is something that we might need in the future. So it's sort of like the to-do list, how to make this embedding properly, but until now we have not used it.
Okay. So we will have one more last question from Miguel Diaz. I would like to know, what work are you doing to improve the Shark LVC timescale? Can we wait to increase timescales in the near future?
Okay, so this LVC is something super new, and of course now I just put you the best face of it, but there are also problems. And what you are referring to is even like an obvious problem, right? I mean, because in principle there is no trouble to propagate much longer, right? But the question is how long these harmonic potentials are going to hold, right? Because if eventually you just go out of the region of these harmonic potentials, then your dynamics is going to be wrong. So the only way to solve this is just to introduce some unharmonicities in the potential. So this comes at a cost, this comes as a trouble, and but if this is useful because you really need to go beyond like what the harmonic potentials are holding, then this is necessary. So we have plans to maybe to go from LVC to QVC, so to instead of linear, just to have quadratic bionic couple models. for cases where linear Baronian coupling is not good, right? So this, yeah, is in plan, and we will see how expensive this is. I mean, what is the price? There is never a free lunch, right? So we will see what's the price of this and whether it allows you to go to longer time scales, and hopefully we can afford this.
Maybe one very last question from Nikolai Kondratyev. How many picoseconds one may need to model to understand probability of certain trajectory for molecular switch photoisomerization?
I don't think that there is a universal answer to this. I mean, in the way that I understand this, so like probability. So one thing is like you need to have a substantial amount. I mean, a large enough ensemble of trajectories in order to have some statistics which make sense. Now, if the process takes place, I mean, many of these photoisomerization processes, they are really like femto ultra fast processes, and therefore even with on the fly, I mean, people have done like enough propagations, but at the price of very few trajectories. You would need more trajectories, and you would need it. I cannot say, because most of them, they are ultra fast. Now the problem is photoisomerization cannot be done straightforward with LBC. So that's an example where if we would like to try something like that, then probably one has to take some of the important modes for this isomerization in a different way, but you cannot describe an isomerization with a harmonic oscillator. So this has to be done in the best case on the fly. And then somewhere you need to pay the price, either few trajectories, short trajectories, or low level of theory, right? So you can push it. It depends really on the specific example, I would say.
Okay. So thank you again, Leticia, for this great talk, and thank you.
You're welcome
For asking questions. And so I think we come to the next speaker. Suzanne, are you going to introduce?
I will. Hello, everyone, and thank you again, Leticia. I'm delighted to introduce our next speaker, Professor Ryan Chenery, who earned his PhD in 2008 at Scripps Research. He then moved on to an NIH postdoctoral fellow at Harvard, and then in 2010 moved back to Scripps Research, where he began his independent career, and that followed soon after with tenure in 2014. Ryan's lab develops new chemistry to quickly access natural product chemical space and collaborates with biological labs to explore the functions of these natural products. So he'll talk to us today about the chemical synthesis of secondary metabolites. The floor is yours, Ryan.
Well, thank you, Suzanne, for the very kind introduction, and thank you for the opportunity to speak here today to an international crowd. This is a real thrill. And thank you for the invitation to join you as a member of the Scientific Advisory Board. I'm a strong advocate for chemical synthesis broadly. And that includes methodology, mechanism, and total synthesis, and we do a little bit of all those things in my lab. I'm also a strong advocate for caregivers that have dual responsibilities in both their academic career or with their family. I'm the father of 4 young kids, or as we call them nowadays, vectors, and I've seen firsthand how difficult it can be to balance the responsibilities of these 2 high-intensity activities. For those of you in the audience, if you are interested in joining me in some endeavors to try to help those who are caregivers of elderly parents or children or disabled family members, please reach out to me and maybe we can figure something out. So as I mentioned, my lab has several different activities that we're involved in, including transition metal catalysis, the interrogation of biologically active natural products, especially those that are active in the central nervous system of mammals. But today I'll tell you about a very fundamental problem in organic chemistry, sometimes referred to as the attached ring problem. That is, how do you establish with high stereoselectivity stereocenters at the bridgehead position of tetrahedral attached rings? And this program comes from our work in natural products, which are important because they occupy areas of chemical space which are completely different than those occupied on average by chemical feedstocks, referred to here as synthetic compounds, by approved drugs, most of which are derived from chemical feedstocks, and instead embody molecular parameters that can often provide them an advantage for therapeutic development, including high aqueous solubility, inherent compatibility with the cell, and especially structural complexity, which can impart specificity of binding in the cellular environment. So the more complex a small molecule is on average, the less promiscuous it is, and the more likely it is to find a specific target in the cellular milieu. So we think about these activities as navigations through chemical space, with the idea that if you can access these areas that are remote from commercial feedstocks, and you can access them efficiently and potentially better than anyone else in the world, then you're poised to discover biology that no one else could discover. Now, often that requires or occasions the invention of new chemical reactions, which allow you to navigate the space much more quickly and therefore explore more and discover more. Today, I'll tell you about some of our work on the illicium terpenes, sometimes called the neurotrophic sesquiterpenes, due to their ability to promote neuron outgrowth in primary cultures of cortical neurons. And we have a working hypothesis that the neurotrophic activity derives from hyperexcitation of cells due to antagonism of GABA A receptors specifically. And that derives from their structural overlap with known antagonists that are actually toxins, including picrotoxin and anistatin. But you can see in this microelectrode array analysis that jadophenolide is quite efficient at inducing hyperexcitation of cells. So we were able to access jadophenolide and D-benzoyl tachyronin, which are representative members of this class, by heterobutenolide dimerization, where you have an electron-rich butenolide, electron-deficient butenolide, and they selectively heterodimerize with high stereochemical control and high yield to give you selectively this anti-diastereomer and not the syn-diastereomer. And we're going to use Masamuni's anti versus syn nomenclature here for you nomenclature purists in the audience. I know there are problems with this given that they're cyclic motifs, but let's set that aside for the moment and just use this as a handy nomenclature. And today I'll tell you about a story where we were able to overcome the selectivity with a different strategy, where instead of forming the bridgehead bond, we're able to selectively functionalize a bridgehead by engaging the C face over the Re face to access the syn-diastereomer. So our long-term goals in this area are to strongly tie or interrogate the hypothesis that GABA receptor antagonism is tied to these neurotrophic effects. Right now, this is a correlation, but not necessarily a causation. And we think there's great potential at looking in this area. And that's required us to access diverse analogs and diverse chemotypes for this kind of activity. And we think this has real promise because there's very important applications if you can achieve subtype selectivity for GABA receptors found in the mammalian brain, which, depending on their subunit composition, are asymmetrically distributed. This is images of slices of a rodent brain, so that if you can target one type of GABA receptor, you can target one specific area of the brain. So we did early work here with Eli Lilly. Unfortunately, they reduced their neuroscience division in Indianapolis. So unfortunately, we're in search of a long-term partner. We've, in the meantime, engaged Professor Marissa Roberto, a colleague at Scripps, who's an absolutely incredible neuroscientist and works in GABAergic circuits. And if you ever get a chance to meet her, she's full of energy, and it'll be a memorable experience, I'm sure. The GABA receptor is a fascinating receptor because you can think of it as a combinatorial receptor. You could say its unique identity is not encoded specifically by the genome, but rather the individual subunits are assembled in the membrane to give you this combinatorial array of different types of receptors. So we are trying to match that combinatorial array of receptors with a combinatorial library of these channel binders based on bilobalide, picrotoxinin, as well as jadophenolide and D-benzoyl tachyronin. And we've attempted to do this by taking polyoxygenated building blocks and efficiently combining them together to access these chemotypes. So as I mentioned, we did this in the context of jadophenolide. via a heterobutenolide dimerization, where we start with a chiral butenolide that's electron rich, deprotonate it to form the alkoxyfuran, and add it to an electron deficient butenolide. Reacts selectively and faster than proton transfer, I'll show you, to, in this one step, make the entire scaffold of jotaphenolide. And then that requires just a handful of steps to access jotaphenolide itself. In a single pass from citronellal, we can make 1 gram of the material. We've distributed this material pretty broadly for biological assay and study and application, and we still have something like ½ gram of it sitting in the freezer, if you're interested. We were able to apply this also to the synthesis of dideoxyhydroxy pseudoanisatin, which it turns out we discovered is the chain tautomer of dibenzoyl tashironin. You can affect this isomerization with tosic acid. I won't go through all of the details here, but please see this Jack's paper if you're interested. But the important part of this dimerization is how unique it is, because it's able to forge these 2 vicinal fully substituted carbon atoms that are bridgehead atoms on this attached ring motif. Attached rings are one of 4 different combinations of ring systems to give you polycyclic or bicyclic motifs. So this includes bridging polycycles, which share 3 or more atoms, fused ring bicycles, which share 2, spirocycles, which share 1. The attached ring motif doesn't share any atoms actually, but it just shares a valence bond between the 2 bridgeheads. Now, of course, many of you are familiar, and you've probably made yourself, attached ring systems by way of a biaryl bond formation. These are very easy to make now due to the advent of cross-coupling in the 1970s by Suzuki, Negishi, Kumada, and really nice variations more recently by Dan Wykes. But because these biaryls are now so easy to make, they're kind of like choking up the combinatorial libraries that are available in industry, to the point where, at least in 2015, AstraZeneca took a look at its combinatorial library, and nearly 15% of all the compounds in their library were biaryls. So they're very easy to make, but there is not a general competent cross-coupling to access these tetrahedral attached ring motifs, in particular because of the steric hindrance, but also because of the stereo control. So this butenolide heterodimerization is unique, and we were very interested in exploring it further. And this formed the bulk of a PhD of a fantastic student, Benjamin Huffman. I like to refer to him as the chemistry karate kid for a few different reasons. Number one, because he's an absolutely phenomenal synthetic chemist. This guy's a synthetic chemistry black belt. And number two, I think he kind of looks like Ralph Macchio. I don't know what you all think. And number three, because he says I'm always dating myself with references to the 1980s, which I clearly am now as well. So the first thing we wondered about this reaction is whether it is so competent because it's driven by strain release. As you can imagine, when you deprotonate this butenolide and form the alkoxyfuran, you have these two 5-membered rings fused together, and potentially it's a strain system that can be relieved by this dimerization. And we quickly were able to answer that question as no, because if you use a simple butenolide anion with no other fused rings, the reaction works quite well at -78 in THF. It forms in high ratio the butenolide heterodimer. And one of the things that we noted is that the reaction is both fast relatively and fast in an absolute sense. That is, it's fast relative to proton transfer. This electrophilic butenolide has gamma protons that are about 10 pKa units more acidic than the conjugate acid of the electron-rich butenolide, and yet bond formation to form these two fully substituted centers occurs very efficiently. And number two, it's fast in the absolute sense in that we noticed within 5 seconds the reaction was completely done at 0.1 molar molarity of the substrates. If we dilute the reaction further, the reaction works just as well. And we were curious to know if it could outcompete even proton transfer from an exogenous acid. So the first thing we tried was 1 equivalent of methanol, and the reaction works reasonably well, 55% yield in the presence of methanol. So we tried to push it a little bit harder and found quickly that if we added 1 equivalent of acetic acid, the reactions still work just fine. This is a real quench, a real competition in that we get increase the concentration of acetic acid and the yield decreases. And just to make sure the acetic acid wasn't freezing out at cryogenic temperatures, we added acetic acid to the nucleophile prior to the electrophile, and then added the electrophile, and it completely stopped the reaction. So this is a true competition that we're observing. Remarkably, if we use 2 equivalents of HCl in methanol, admix them with the electrophile and add the nucleophile, we still see a 30% yield of the butenolide heterodimer. Again, it's a real quench, so if we add the electrophile second, then we see no reaction. And remarkably, if we prepare an aqueous solution of the electrophile and add the lithium enolate to that aqueous solution, we still see a 37% yield of product. So this is really surprising in the efficiency and the speed of this reaction of the lithium enolate. So we were interested in studying this reaction in situ to see if we can actually determine the half-life and the rate constant, assuming a 1-to-1 stoichiometry in for the rate determining step, which is actually an incorrect assumption, which I'll tell you about. So here is a React IR trace starting with the electrophile. Here on the left-hand trace, the electrophile is shown here. We add nucleophile at this time point, and immediately we see product, and electrophile is gone. We don't even see nucleophile. Okay, so within 1 second, which is the scan rate of this React IR, we see complete consumption of starting material. Same if we start with a lithium enolate, we add electrophile, and instantaneously the enolate's consumed. So this reaction then, it must have, again, assuming a 1-to-1 stoichiometry, an observed bimolecular rate constant of 1,000 per molar per second. Okay, it turns out actually it's faster than that because it turns out it's actually a 4-to-1 stoichiometry, so the enolate concentration is lower than what we think. The activation energy is less than 9 kilocalories per mole then based on that rate constant, but we can't exactly tell what the rate constant is. This is the ceiling, again, because the scan rate obscures the half-life. So we went a little more extreme, and we started with very small quantities of the lithium enolate and the electrophile. We injected them simultaneously into a large volume of THF at minus 78 degrees. We did 5 seconds and then quenched with 10 equivalents of HCl. And it had a reasonable error in the yield that allowed us to sign a half-life of approximately 1.7 seconds on average at 100 micromolar. So this is 0.0001 molar. And at 20 micromolar, we see a concomitant increase in the half-life to 10.4 seconds. That allows us to approximate a bimolecular rate constant of 5,000 to 6,000 per molar per second, and then an activation energy of less than 8 kilocalories per mole. All right, so that's pretty fast, but let's, how can we calibrate our intuition for how fast that is? So we turn to some of the lithium enolate literature. This is a beautiful paper by Hans Reich, who used his rapid inject NMR apparatus to determine the rate constant for an acetophenone enolate reacting with a benzaldehyde electrophile. And they determined from the dimer aggregation state of the lithium enolate that the rate constant was 5 per molar per second, and that was actually at the limits of measurability of their rapid inject NMR. And here the butenolide dimerization, which is forming, again, vicinal fully substituted centers, occurs 1,000 times faster than an unsubstituted lithium enolate. So how does this reaction work? So we took some time to try to understand what the rate determining step was and why the reaction might be so fast. One of the first things we observed is that all the heavy atom isotope effects associated with carbon are near unity. And assuming this is an irreversible reaction, which it appears to be because the dimer doesn't degrade under the reaction conditions, if it's irreversible, that means that the rate determining step must precede carbon-carbon bond formation. We observed a relatively low but positive Hammett value, rho value from that Hammett plot. Is significantly lower than that of a 2-electron microreaction, but it still is positive, and I'll come back to why that surprised us. There was nothing unusual about the aggregation state. We used David Collins' beautiful lithium-6 job plot titration method to determine that the lithium enolate of the butenolide exists as a qubit tetramer, which is a fairly common aggregation state of lithium enolate. And from this data, then we came up with 2 hypotheses that we felt were consistent with the data so far. The first was that potentially the electrophile engages the nucleophile and undergoes a single electron transfer to generate this biradical, which then collapses to form the product. One of the reasons we thought this could be a single electron transfer mechanism was, number one, the lack of a carbon isotope effect if the carbon's undergoing bond formation. But number 2, the nucleophile would react with single electron oxidants like tempo, which lithium enolates tend not to at minus 78 degrees. 2 equivalents of tempo deliver this tempo adduct. And nitromethane, not nitrobenzene, not nitrosobenzene, but nitrobenzene delivered this adduct, which is really surprising and suggested to us the single electron transfer mechanism. The other possibility was that is not the tetramer that reacts, but instead a different aggregation state, and that aggregation state change might be induced actually by the electrophile that then is added to deliver the product in a very fast and apparently non-rate determining carbon-carbon bond formation. So we turned to Ken Hauk and Shuming Chen. They're just up the road in LA, very nice to work with. And I think this is our second, let me see, we've had now 3 papers with Ken Hauk, and I always enjoy working with him because he never tells us what we want to hear. He always thinks about things from a very unique perspective, which I enjoy greatly. So one of the things that we determined, or that he and Shuming determined, was that the tetramer itself was not competent to react in this reaction. The energy barrier was prohibitively high if you compare it to the experimentally determined or highest energy barrier determined experimentally. Similarly, the dimer was too high, but the monomer had this remarkably low 4 kilocalorie per mole activation energy. And partly that's so low because of dispersion forces that lower the energy barrier via pi complex formation between the nucleophile and the electrophile with just absolutely perfect orbital overlap in the transition state. The other thing that we determined is that this deaggregation was unlikely to occur spontaneously, and there was no evidence of that from the NMR either, but rather it needed to be assisted by the electrophile in order to deaggregate to a monomeric free transition state complex. And then thirdly, we determined that the diastereomer likely arose via secondary orbital interactions between the acyl group and the C2 position of the nucleophile. This is a little bit hard to see on the slide, but I'm going to come back to this later in a different context. All right, so the reaction is extremely efficient by virtue of this perfect complementarity between the pi systems. I deliberately made the substrate scope too small to see because I think the important thing about this reaction is how it relates to biaryls and formation of libraries. So we can analyze the substrate scope not by the different variations we can make to the components, but rather how they occupy a shape space defined by principal moment of inertia, where you can define linearity, spherical nature, or a disk shape. If you look at Chembl, which is a database of bioactive small molecules, all of these drug-like molecules tend to line up to be very simple and flat, as is their stereotype. But if you look at the butenolide heterodimers, they occupy a really diverse range of different shapes, from linear to disc-like and to spherical. And in terms of their relevance to biology, we found in collaboration with Professor Luke Larison, who's also just a phenomenal colleague and a lot of fun to work with, that these compounds are pathway selective antagonists of CGAF sting. They appear not to be non-selective, in that there are many different inactive heterodimers, but heterodimers that bear para-substituted beta aryl motif are fairly active antagonists. So I'm going to come back to this and why it's important, but hold that thought. All right, so of the many chemistry problems that remained, one of the most significant was that while the butenolide heterodimerization was quite anti-selective, we could never obtain a syn-selective reaction where this alternative diastereomer predominated, no matter what we changed about the substrate or conditions. And this was, on the face of it, the most obvious reason this is important is that while we could access jadophenolide and dibenzoyl tazzaronin efficiently from this butenolide heterodimerization, we could not access other congeners like ilisamonin and merolactone that embodied this syn stereochemistry at the 2 bridgehead attached rings embedded in this ring structure. So the question is, how can we reverse the stereochemistry, or maybe what if we reverse the order of bond formation? Will that allow us to reverse the stereochemistry? So what does that mean? If we disconnect the 2 butenolide ring systems at the bridgeheads, we get back to the butenolide monomers, and we've shown that you can access the anti-stereochemistry through this conserved transition state. If, however, we change the order of bond formation and we start with an attached ring motif and then add in one of the substituents to form a quaternary or fully substituted carbon, potentially we may not solve the problem, but we've at least changed the problem and maybe allowed us to address it from a different perspective. But the problem now is that we have to engage one rotamer of the attached ring motif. So we've modeled it simply with enol tautomer of the butenolide. And here you can imagine free rotation of this carbon-carbon bond. If we engage the reface, that will allow us to access the anti-stereochemistry, which we can already do with the butenolide dimerization. But if we can access selectively the C face, now we can maybe access the syn diastereomer. So this is a simple enough experiment, which is really important because in most cases, your ideas in research will fail. And as a result, it's really important to fail fast. And for better or worse, we failed very fast. We could test this very easily by taking the parent butenolide forming the lithium enolate, adding it to the thioester of our standard electrophile. It'll become clear later why we use the thioester. This gives us high selectivity according to our previous model of pi stacking. And then we methylate the alpha position of the 1,3-dicarbonyl to form a new quaternary carbon. And that is simply because this quaternary carbon is found in the illicium terpenes. Okay, now we're poised to form the new butenolide enolate and test bond formations. We chose to use a Michael reaction with methylvinyl ketone simply because that was well precedent to be gamma selective for butenolides. And using DBU as the base, we see actually a good yield and very high stereoselectivity. But for the wrong diastereomer, it gave us again reface addition and a high ratio favoring anti over syn. And our misery was solidified or crystallized, you could say, by X-ray analysis of the product to determine definitively that this was the stereochemistry. As you can imagine, it's a little bit hard to assign stereochemistry given the rotational lability of those ring systems. Okay, so we're in a bit of a conundrum here, and we're searching for different strategies to solve this problem. And the first thing you consider when you think about changing selectivity of anti-syn ratios with lithium or enolates in general is you think of closed versus open transition states. Okay, and this is based on work, beautiful work by Howard Zimmerman and Marjorie Traxler back in the 1950s, where they developed a model to explain why you saw syn selectivity for Z enolates, anti-selectivity for E enolates. And they proposed this 6-membered ring, Zimmerman-Traxler now, we call it a transition state to explain that selectivity. Interesting kind of historical note here. This model was built literally, okay, with wooden models. You can read about it in a footnote in this paper. They used the Fisher-Hirschfelder models to construct the system. They had to model actually the coordinated carbonyl with an imine because coordinated carbonyls were not available in this wooden set. And the magnesium atom that was chelated between the two oxygens, they modeled with a tetrahedral carbon because they didn't have metals in the set. So anyway, just a fun historical note. Now, we lucked out here a little bit, at least in our initial thinking, because by definition, we're stuck with E enols or enolates because they're cyclic, okay? And so that was potentially good for us because E enolates show opposite selectivity between closed versus open transition states, in this case in a Mukayama aldol fashion. So we thought potentially we could reverse selectivity if we silated the butenolide and engaged it in a Mukayama type microreaction. But okay, this is a very much forced analogy. Okay, there are many problems that you immediately are picking up on. Number one, we're not performing an aldol reaction. Okay, we need to look at a Michael reaction. Number two, we're using DBU to form the enolate. That would be a naked enolate, or at very best a weakly hydrogen bonded enolate. There's no metal in sight, and therefore we're not dealing with the closed versus open transition state. We were already dealing with two open transition states in non-aldol, but instead Michael reactions. Okay, but sometimes it's okay to make mistakes, and what I try to emphasize to my group anyway is that it's important to make good mistakes or mistakes in the right direction. That sometimes is very hard, but sometimes even wrong thinking can point you in the right direction. And here it helped us a lot actually, because we thought, well, silation may not lead us to a new, from a closed to an open transition state, but potentially it could perturb the selectivity of these, the rotational isomers between Re versus C exposure. So in the C phase, we have the thioester and now the silyl group pointing away from one another, whereas in the Re phase, we have the silyl group and the thioester pointing towards one another, and potentially that could be sterically penalizing, and it may favor then the C phase. Of course, this is strictly considering ground state. It is not a transition state calculation, but the reason that this may correlate somehow to transition state geometries. So fortunately, it was, again, very easy to try this experiment because we could simply silylate the butenolide. We've tried first TMS and TES silo groups, but these were quite unstable. You can imagine this is phenol-like silo ether, and it's also quite electron rich, so it can decompose by protonation. Fortunately, the TBS was stable enough that engaged Michael-acceptor to a small extent. We got 17% yield, but really the triisopropyl silo worked very well. And we obtained between 57 to 65% yield, depending on order of addition. And remarkably, very high stereoselectivity, now favoring syn. And so now we've got this complete reversal of stereoselectivity between anti versus syn, depending on whether we use a naked enolate versus siloxyfuran. But the question is, what is the basis for this divergent stereoselectivity? So again, we turn to our friends up the road, and Ken Hauk and a summer intern, Jonathan Wong, who actually now is at Harvard joining the Jacobson lab, and now Shuming Chen, who's at Oberlin College starting her independent career, helped us out with these computations. This was actually not very easy to do and not very clear from the outset. So I'm really grateful that they worked so hard to put in the hard work to figure this out. So in the case of the DBU conditions where we have a naked enolate, it turns out that the main stereochemically defining interaction is between a beta methyl group on the gamma lactone and the incoming methylvinyl ketone, which disfavors the C phase addition. Okay, there's just a closer distance in C phase compared to rephase. Now, why is that? The reason is that the MVK electrophile approaches in a Diels-Alder-like transition state, you can say. Again, you have a secondary orbital interaction between the alpha position of the butenolide and the carbonyl carbon of the MVK that requires it to adopt a particular conformation. And in the case of the C phase addition, then causes a steric clash between the beta methyl group and the beta group of the MVK. Okay, now the situation is similar, but with a bit of a twist in the Mukiyama-Michael reaction. So in this case, again, as we suspected, the silo group wants to point away from the thioester. I'll start here actually with the C phase addition, which is favored. I've drawn out the thioester a little bit more explicitly here in the ChemDraw version. You can look at the 3D models if that helps. But the thioester points away from where the triisopropyl silo group points, again, to alleviate any steric clash. Because the triisopropyl silo groups points to the left, the titanium tetrachloride coordinated to the oxygen now points to the right. Okay, so now they can all stagger or splay apart from one another in this alternating distribution of steric bulk, and that allows in a productive transition state, and that favors the C phase because let's look at what happens to the rephase. And the rephase, similarly, we have alternating thioester on the right, triisopropyl silo on the left, and then titanium tetrachloride on the right. But now, because the thioester is always on the left, now the TIPS group points in the opposite direction of the furan, oxygen in the ring, and this requires now the titanium tetrachloride bound MVK to adopt an exotransition state. And now you no longer can benefit from a secondary orbital interaction with the carbonyl carbon. And so now the key is that it's not necessarily a steric clash which determines the selectivity, but rather it's a secondary orbital interaction which determines selectivity for the C phase. Okay, so with all this in hand, now we're able to apply it for proof of principle, the synthesis of merolactone A. We start with our standard sequence of butenolide addition. In this case, now we reverse the order a little bit. We silylate first and then methylate the 1,3-dicarbonyl. We can then affect a Mukiyama-Michael reaction with high selectivity for a syn. And now, in a very important step, which required the thioester, we used Justin Dubois' beautiful ACL Heck chemistry. There's really nothing like it in the literature, actually. This is a very unique reaction, and it was uniquely effective to form the tricycle of merolactone A. Now, this is a little twist of fate here. The first author on this ACL Heck chemistry from the Dubois lab is Arun Latunkara. Actually, he worked for Denali, which is the company that Ben ended up joining. Maybe that was coincidental, maybe not. It's a great company and working in neuroscience. Check it out if you don't know them. I met Arun a couple years ago and was really impressed with their science. From the ACL Heck product, we're able to engage this material in a Lusch reduction, relieving a significant strain that's imparted by the really 4 or 5 sp2 atoms all in a row here. And then samarium ketyl-mediated Giesa reaction closes the fourth ring of merilactone, which completes the formal synthesis according to Hong Benjai's beautiful work in Angewandte a few years ago. Now, when we were undertaking this work, there was also another beautiful synthesis that came out from Zhang and Jack's, I think in January. And they reported something really, really interesting and a little bit ironic. So merilactone A is unique among the Illicium neurotrophic sesquiterpenes in that Inoue about 10 years ago had determined that the enantiomer of merilactone A was apparently also active as a neurotrophic agent, which is really surprising, and it was justified based on this pseudosymmetry of the merilactone scaffold. But what Jiang found actually is that merilactone is essentially devoid of neurotrophic activity. Okay, it's almost identical to control, which in some ways makes more sense and is consistent with the operational and statistical difficulty of this neurite outgrowth assay. Now, jadophenolide, as you can see, as a positive control, is quite active in promoting neurite outgrowth. So as far as merilactone A as a target for exploring neurite outgrowth goes, it's probably not valuable. But remember that our interest is actually more in C-gas sting. And what we found to our great interest was that in some of the series of C-gas sting antagonists, actually the syn stereoisomer corresponding to the merilactone A stereochemistry was active, whereas the anti-stereochemistry was not. So we actually really needed access to this alternative diastereomer. So anyway, that concludes the talk. I thought it was appropriate for today's seminar. This work just appeared in Angewandte. I think we just got the galley proofs this morning, actually, so we'll get those back soon, I promise. Oops. And I want to thank my group members for their extremely hard work. I want to, in particular, thank Ben Huffman, who is, as I mentioned, at Denali now. Yusuke Hanaki was a great Japanese postdoc who joined us to help with his work. And Tiffany Chu is actually, I guess she just started her second year of graduate school, and she joined us during the pandemic period where we were working in shifts, and she was working her hardest to get this paper across the finish line. So I'm really grateful for her hard work under very difficult circumstances. And I have to thank other people who have worked in the butenolide and neurotrophic sesquiterpene area. Thank you again for the time and the opportunity, and I'm really happy to take questions.
Thank you very much, Ryan. Fantastic talk, and no rush on the galleys.
Thanks, I appreciate it.
Let me see if we have any questions. We have a comment from Pankaj Mahajan. Great work and a great talk. You are also a black belt in synthetic organic chemistry.
Well, I have to be a black belt in something. I'm the most uncoordinated person you'll meet, so I won't get it in actual martial arts.
Let's see. So anyone in the audience, please do enter your questions for Ryan in the Q&A window, and we'll pass those on. And just for my curiosity, I'll throw in a question. That Heck reaction, the acyl Heck reaction with the thioester, mechanistically, I'm not up on my Heck chemistry, the copper, the role of the copper salt.
Oh, great question. Yeah, so I suspect, I think this is consistent with Justin's paper, that it either labelizes the thioester, or potentially it initially inserts into the thioester, then transmethylates the palladium. Maybe similar to
Leviskind. Is that right?
Exactly. Yeah.
Okay.
Thank you. I actually was searching for the name. Yeah.
I wasn't sure, and I had, that was popped in. Okay, great. Not seeing any questions in the chat. So I'll throw another one at you. For the analysis of the C-face orientation for the syn to obtain the syn product, the secondary orbital overlap obviously plays a key role, but did you see any other kind of interactions with that? I couldn't see in that diagram with the benzyl group on the bioester. Is there any stacking?
Yeah, that is a great question. We went back and forth a little bit to see if there was any, because initially that was our working hypothesis. In fact, this was modeled without the phenyl ring in place, just to reduce the computational load. There is a weak interaction between the CH bond of the thioester and I think it is the butenolide ring, but probably doesn't contribute very much energetically. So the predominant energetic interaction was exo versus endo, but originally this distant effect from the thioester was one of our working hypotheses.
Thank you. There is one question that has shown up in the chat from Cheng-Ying. Thank you for your talk. You mentioned the pi-pi interaction was involved in dimerization. Do you see a difference from the yields of substrate scope, electron rich versus core?
What an insightful question. Yes, we do. And I didn't discuss this in detail in the talk, but we do discuss it in the paper. And it was a real sticking point in settling on the mechanism, because as you notice, what we saw from the Hammett plot was slight positive slope. And what we expected to see, actually, if the electrophile caused deaggregation, we expected to see a negative slope, because you'd expect then that the more electron-rich electrophiles would chelate the lithium better, distantly through resonance with the aromatic ring. However, because there was this pi stacking interaction that seemed to play a major role in the rate determining step, actually, sort of retrospectively, when we revisited that data, it makes sense that electron withdrawing groups will actually accelerate the reaction because they strengthen the pi-pi interaction, even if they weaken the chelating interaction with the lithium. If that makes sense, which is maybe why there is a relatively weak Hammett slope.
Thank you. And one final question before we move on from Hira Khalid. My question is that in project you envisioned, if you are facing time issues and of course not getting desired product, what's your strategy to deal with that?
Oh, that's a difficult question. My go-to reference for this actually is one of my favorite books. I don't know if I have it. I think it's probably on my bookshelf. Baron Carpenter's Determination of Reaction Mechanism. And I love how realistic he is in the introduction to that book when he talks about determination of reaction mechanism, which of course, as he points out, is not inherently true because you only determine what is not the reaction mechanism. Oftentimes you exit this discovery cycle not when you finally determine, yes, this must be the only hypothesis that works, but sometimes as practical as we have to publish this paper, the student has to graduate, or I'm just really sick and tired of this project. So that's a great question because there's no one answer. And I would say you have to balance multiple different priorities, not just obtaining high yield and good selectivity of the final product at any cost. At some point, you do have to graduate.
I would agree. So thank you again, Ryan, for a great talk. And we'll move on to our next speaker.
Thanks, Suzanne.
Yep. Professor Jianghong Rao is our next speaker. He obtained his PhD in chemistry from Harvard University in 1999, working on oligomeric derivatives of vancomycin with George Whitesides. And then he moved to the University of California, San Diego, to Roger Jian, where he joined the Department of Molecular and Medical Pharmacology as an assistant professor in 2002. In 2004, he moved to Stanford University School of Medicine, where he is the professor of radiology and chemistry and a faculty fellow of Stanford Chem. His research areas include chemical biology, molecular imaging and sensing, bio-nanotechnology, biomaterials, and cancer theranostics. I'll hand over to you, Jianhong.
Great. Judy, thank you for the kind of introduction. And we're down to the last talk today, so if we can stretch a little bit and while I'm setting this one up. Can you see my screen well?
Yes, it looks good.
Okay. So exciting to be part of this symposium and to share some of our work in developing chemical probes for bioimaging and biosensing living subject. And so I'm trained as a chemist, and now I'm working in the interface between chemistry, biology, and our research is primarily focusing on developing imaging probes for imaging application and for cell imaging and also animal imaging. Eventually, we hope some of them can move to the clinic for clinical imaging. So I want to touch, wait a second. So I'm going to use the cursor, see how this one works there. So I'm going to touch a little bit on this, why we bother to imaging. So imaging biological molecular processes in space of time made great contribution to our understanding of biology and physiology. And so a lot of the imaging modalities have been developed and to enable this ability. And with those imaging modalities developed that allowed us to image amazingly wide in the scope of the subject, from very small size to the nanometer all the way to the millimeter size. Oops, this is too sensitive, sorry. And so with the size of the imaging subject increase, so is the complexity of the system. For example, if you look at yeast cells, one single yeast cell contains millions of the protein molecules. And then when you go to the human cells, the number is even much bigger, go to billion. And the human body contains trillions of cells. So with that complexity, how can you image a subset of the molecular cells out of the billions and the trillions of others? And that specificity comes from molecular probes. And I highlighted two examples here. One is genetically encoded GFP, used here to highlight the subset of group neurons in C. elegans. And the other one is the FDG molecules used in clinic and the chemical probes to highlight the tumor cells and by physicians. So genetically encoded reporters like fluorescent protein and being well appreciated by biologists because the genetic encoding by a single DNA sequence make it really easy to do the tissue targeting. On the other hand, because of the fluorescent protein can only be imaged optically, and they have very limited tissue penetration. And then you can only image those fluorescent protein, you cannot image the endogenous protein. And that comes to chemical probes. And you can design them to image many different endogenous targets, like from surface receptor and the enzyme activity and the messenger RNA and the transporters. So that greatly expand the imaging scopes and the target. And you can also design the probe to image and deep tissue imaging modality like MRI and then PET. On the other hand, one of the big challenges with the chemical probe is designing the probes with high specificity for imaging target. So in this talk, I'm going to share some of our work in imaging the enzyme target and ability to imaging them at the course of the different imaging modalities, and also how to improve, the specificity of the imaging probe. And also like to share that our experience working with a nanoparticle-based platform to image non-enzyme targets. And so first on the beta-lactamase, and the beta-lactamase can hydrolyze the lactam antibiotics, and the lactam antibiotics are the most prescribed antimicrobials treating infection. And expression of beta-lactamase is one of the major lactam resistance mechanisms by bacteria. And that gives us the strong motivation to detect beta-lactamase activity in biological samples. And the later history and the development of phlorogenic beta-lactamase probes. And one of the early examples was reported by Roger Jian almost 20 years ago now, and is based on the structure of cephalosporin. And if you have a good leaving group attached to the 3' position of the molecule, the hydrolysis would lead fragmentation release of the actual group. And based on this chemistry, many beta-lactamase probes have been developed. And some of them shown here, developed by us, and you can find more from the reference list here. So with those probes, we tune up the linker chemistry and the fluorophore, and near-infrared probe here allowed us to extend the imaging from cell imaging to the animal imaging. And the bioluminescence probe shown here allowed us to perform the bioluminescence imaging. However, those probes do not display beta specificity for any beta-lactamases, and it's a broad spectrum the beta-lactamase probe, and there are over hundreds of the beta-lactamases reported so far. So we are particularly interested in two types. One is carbapenemase, another is the BLAST-C. So I'm going to focus a little bit more on BLAST-C. BLAST-C is expressed by Mycobacterium tuberculosis. The bacteria causes a lung infection of tuberculosis. So because the BLAST-C is expressed by Mycobacterium tuberculosis, which invited the hypothesis that a BLAST-C specific probe may be useful for the TB diagnosis. And showing here is the structure study by our collaborator, Jim Sargentini at the Texas A&M, and the structure of the BLAST-C compared with another class A beta-lactamase, TM1. So they have very similar structural loop conformation as shown here, but there's a key mutation in BLAST-C, which is residue 164 from arginine in TM1 to alanine. Because of this mutation, BLAST-C lost the soul-bridge interaction, make this loop is very flexible when open up binding to the bulkier lactam substrate. And guiding by this structure inside, we start to play with modification on the lactam structure. And one of the introduction we made at a certain position with substitution of methoxy group, and another position at the 2, and with a different substitution like here, cyclopropyl group, and that dramatically improved the specificity of the structure for BLAST-C, and that leading into CDGC, which is very specific for BLAST-C comparing to the other beta-lactamases we tested. And this exercise can improve the specificity of the substrate, but we are mindful of the large number of the beta-lactamases. So this specificity may still not be enough for the TB detection. And so we sought a new approach to enhancing detection specificity. And that comes what we call the dual targeting strategy. And in these cases, we designed a probe to be activated by BLAST-C and another target called the DPRE1. And this is a key enzyme involving the mycobacterial cell wall synthesis. DPRE1 is also a promising target for development of anti-TB drugs. And one of the lead structure contains a moiety of the dinitropentane group. DPRE1 reduces one of the nitro group to nitrosyl, and then further interaction with the cysteine in the pocket and form this covalent adduct. And that allowed the attachment of the fluorophore to the protein. So we characterize the system, the probe, with the number of the the bacterial strands and the biochemical assays showing here is indeed 2 targets are required for the labeling with this bacterial BCG. And this video shows the labeling of the BCG rapidly, and you can see that it could occur even within a few minutes. And we can also adapt the system to microfluidic chips platforms. And this, let me see here. So you can see there's a bacteria can float on the chips channel and captured by the detection window. And this essentially can enable the system for point of care diagnosis. And we also tested this strategy in another target combination. And here is block C with AG85. This is another enzyme-mediated cell wall synthesis in mycobacterium. In this case, the sugar substrate trihaloate is conjugated to lactam through this fluorophore. And so block C hydrolysis would release this labeled sugar compound and further processed by AG85 incorporated in the cell wall of the mycobacterium. And we applied this compound to image BCG endocytosis by macrophage. And as you see here, the BCG pre-labeled with the red, and the probe can generate a green signal, and the different concentrations are really low from 2 micromolar, 10 micromolar. You can see the good overlap of the labeling those endocytosis and the BCG in macrophage. And this is much better than just a single targeted probe or the trihaloate alone. So we expect that this approach may be applied to other imaging problems, like a cancer imaging that also demands the high specificity. And then next, I'm going to switch to the second target, enzyme target, proteases. And this is another important class of the proteolytic enzymes, and that cleave the peptide bond and the specific size. And this is also a big family of the enzyme with more than 500 members, and it controls and influences essentially many cellular processes. And the list here from DNA replication, transcription, and the list go on and then go on. So we can imagine that. So a lot of the effort have been developed to image the activity of the beta-lactamase, the proteases. The approach are dominated by optical imaging. And one is a substrate-based probe, as reported by Westlander and many years ago. And the other one is inhibitor-based, and the covalent attachment of the probe and then to the enzyme, and as pioneered by my colleague at Stanford, Matt Bojo. And other modalities include MR imaging and have been much less explored. And one such early example here is F19 and the based probe. It would just demonstrate it in vitro at that point, maybe because of the F19 sensitivity may not be sufficient for in vivo application. And a very clever strategy developed by Roger Chan used proteases to gate the cellular uptake of cell-penetrating peptide. And by doing this, you can attach different imaging tags from fluorescence and to PET and MRI. But this approach is essentially limited to the extracellular proteases. So at that point, we are interested in developing a general strategy and compatible with other imaging modalities. So our idea was that the probe and then get it into the cells and activated by proteases, and they cleave the product and starting to interact with each other and self-assemble and generate a larger species. And that would lead to the retention and the imaging contrast. And so to realize this conceptual design, and then we turn to a very old reaction and used to synthesize the dilute. And the dilute, the substrate of the enzyme flylosylferase, is widely used for bioluminescence imaging. The condensation takes place between the amino cell group of cysteine with benzoyl, cyanobenzoyl, and in short, and it's called CBT. And this reaction actually proceeded really fast, even in aqueous solution. And the second order reaction rate would determine about the 9 per molar per second. And both 1,2 aminosyl and the 1,3 aminosyl can react well with CBT. But if you change the benzoyl with other aromatic compound, aromatic rings, and then the cyanyl group activity is significantly impacted. And this quinoline derivative here displayed 500-fold less reactivity compared to CBT. And this becomes very useful in our probe design. I'm going to talk about later. And so with that, it came to two approaches in our design, probe design. One is intermolecular reaction design, and then the other is intramolecular design. So the first one is we use the CBT and then Maass cysteine group at the amino position and then cell position. And then you have the R3 position allowed you to attach the imaging tag or maybe even a drug molecule. So activation can lead to intermolecular condensation and then further assembly aggregation. The second approach is you take quinoline cell group, and which has a low reactivity with the endogenous system. And this only allowed you to do the intramolecular cyclization after activation and then condensation, and then go on with the aggregation. Because the quinoline cell group has a very low activity for the cysteine inside of cells. So this would essentially minimize the competition from the intracellular free cysteine in cells. So this is preferred for a future probe design, and we use this scaffold for, there's a future generation of the probe, there's a protease probe design. So we have done, the demonstration validation of this strategy with a number of the targets, and I'm going to focus the rest of the validation in this talk with the caspase for imaging and apoptosis. And apoptosis is well-controlled and the cell death mechanism, and many therapeutic compounds act as just apoptotic triggers. And those triggers eventually leading to the activation of the caspase-3 and then cell death. So visualization of active caspase-3 enables early monitoring the effect of the cancer treatment. And caspase-3 cleaves a very specific protein sequence, and DVDX, and the X can be any amino acid, and that provided us the opportunity to design the caspase-3 fluorescence probe. And here is we put the peptide here on the cysteine residue, and then fluorescence dye to the R3 position, as I mentioned that before, and then activation of the caspase-3 remove the peptide, and then reduction, and then cyclization. So we characterized the probe in many in vitro applications, like here, the specificity, reaction kinetics, and here, the aggregation after activation. And then in vitro experiment, imaging chemotherapy by Dr. Rubinson in animal model. So treated tumor is accumulating significantly higher fluorescence signal compared to saline controlled tumors. And if you take the tumor section out and perform the super resolution image and try to see whether the fluorescence particles formed in the treated tumor induced by the chemotherapy. And that's what we've seen that in this video, those green fluorescence particles, you can see that in treated tumor, but not in the controlled tumor. Moving to the PET imaging, you can simply just replace fluorescence with F18 tag, and that allowed you to perform the PET imaging. And showing here is the movie of the tumors received the chemotherapy and image with the F18 tracer. You can see the significantly higher uptake of the activity in treated tumor, but not in the controlled tumor. And we further engineered the scaffold and then leading to our latest generation of the much simplified scaffold. And this the tracer currently with doing clinical trial at the Stanford Medical Center. And we expanded this tracer to image immune therapy in animal model. And you see here that the tumors responded checkpoint inhibition therapy give much higher signal compared to the non-responder and the untreated tumors. So this opened another utility of the probe, not just for the chemotherapy and also potentially imaging the immune therapy. Going to MRI imaging. And so this, we can simply attach and gadolinium again to the R3 position. And for MRI contrast agent based on the gadolinium, the formation of the gadolinium nanoparticle and leading to slow rotation of the gadolinium chelated. And that increased rotation, tumbling time, and then leading out much bigger R1 reactivity. And that's what we've seen that in the in vitro measurement of this probe before and after caspase treatment, leading to nearly double the R1 reactivity. And we test that in vivo as well. And in this case, we applied it to imaging radiotherapy. You can see much stronger imaging contrast in with 7.6 grade radiation compared to the control tumor without radiation, another tumor with control probe, and cannot form the aggregation product. We also apply this to image the viability of transplanted cells potentially in the future cell therapy. And you can see apoptotic the stem cells give much higher, the stronger in the contrast compared to the viable in the transplanted stem cells. Finally, we explored the pre-targeting imaging strategy with our in vivo assembled approach. So instead of having imaging labeled here, so we replace it with the click handle, for example, transcyclooctane and TCO. And the probe first injected and get activated and can form the nano aggregate as the typically other imaging probe. But then you follow it with the labeled tetragen, and the labeled tetragen can come in and then form the conjugate through the click reaction with the pre-assembled TCL nanoparticles. And showing this in the PET imaging study, you can see that this pre-assembled TCO can significantly prolong the tetragen retention and compared to the controls. So a potential advantage of this pre-targeted approach is we can enrich the TCO nanoparticles first before your imaging. You can do the multiple injection, generate a significantly higher amount of this TCO nanoparticles, followed by tetragen imaging. And that potentially can significantly improve the imaging sensitivity. And I show our studies and the results in the previous slides is regarding the caspase imaging, and there are many more other targets that we have imaged. For example, in the other proteases and the intracellular proteases, and even the sugar enzymes. And we also demonstrated that fluorescent modality, PET modality, and many other MR modalities as well, and plus photoacoustic imaging. The applications included cancer imaging, so critical monitoring from chemo, radio, immuno, and also the cell therapy. There are also reports of using this strategy to overcome drug resistance, and by several labs, including one from my former postdoc, Gaolin Liang, and in China. And in the last few minutes I have, I'd like to discuss nanoparticle-based imaging modalities. And this platform over a lot of flexibilities to perform the multiplex imaging and also multi-channel imaging. And the ability for nanoparticles to be retained at the, like I say, tumor tissues, and significantly enhance the retention time, and then allow the longitudinal imaging. So our nano platform derives from semiconducting polymers, and those polymers have a long extensive pi conjugation, and they have a tunable emission. You can just simply altering the polymer chemistry and changing the conjugation structure, and they are resistant to photobleaching and also chemical oxidation. The synthesis of the particles is very standard and well developed and through the nano precipitation. And fluorescence compounds and the sensitive molecules can be loaded through nano precipitation. And pegylation can further render the water solubility and also ligand targeting ability. So the first example I'm going to show is the ability to sense the two different ROS species, reactive oxygen species. And the two modalities we choose to image. One is the fluorescence, the other is chemiluminescence. The differentially can be excluded, and the mutually exclusive optical channels. One need excitation, the others do not need excitation. For the fluorescence imaging, we use peroxide nitride as a target, and a fluorescence dye can react with the peroxide nitride and get degraded and lose of the emission at 820 nanometers. And then you lose of the third interaction between the polymer and the dye molecule. For chemiluminescence imaging, we use the chemiluminescence substrate peroxide oxalate and reacts with the hydrogen peroxide and generate excitation energy. And that energy transferred to semiconducting polymer and generate chemiluminescent resonant energy transfer emission, and that allowed you to detect hydrogen peroxide. So we can further conjugate a galactose targeting ligand to enhance the liver targeting. So we applied this system to image liver toxicity induced by drug molecule. So the first compound we tested is acetaminophen, and you can image the chemiluminescent channel and the fluorescence channel, and you can inject a different dose of the drugs to the animal there. And the second compound that we tested with isoniazide is the anti-TB drugs, and you can also do similarly to chemiluminescence imaging, fluorescence imaging at a different injection dose. And you can see that there's a very different responsive pattern to the different dose injection. And one is the threshold response. The other one is the multi-dose escalation response there. And that indicated the different mechanisms of the drug metabolism. And this makes the probes very useful to study drug metabolism in the preclinical animal models. And the second example is we use phosphorescence probe and with the semiconducting polymer to enable the dual channel imaging fluorescent phosphorescence to image the oxygen level. So the phosphorescence changes at the concentration of the oxygen level, but the fluorescence do not. So you can map the two ratios to detect oxygen level and imaging oxygen level in the animal model. And this can last even over 1 week time window. And you can perform the imaging to study the tumor size effect on the oxygen level and the hypoxia level on the different animal models there. And this could be a very important tool to study this radiotherapy. The last examples I'm going to cover is that cancer binding nanoparticles are made of the fluorescent copper binder CDM showing here, and also a semiconducting polymer. The polymer has a strong absorption in the near infrared wavelengths, And that can provide imaging capability to monitor the drug concentration in the tumor. And the CDM fluorescence can report the status of the copper binding in vivo. And the copper is an important cofactor in many cellular metabolic enzymes. An interesting finding we have with this system is that the particle is specifically targeted mitochondria of the cancer cells. And that allowed the shutdown of the oxidation in the cancer cells and switch metabolism to glycolysis. As you can see, the OCA chain and the ECA chain of the cancer cells. And that causes cytotoxicity to the cancer cells in cell culture and also in the animal model, significantly prolong the survival of the animals with the tumor xenografts. And this is the collaboration we have done that with the UNLED, the Johns Hopkins. We are continuing to explore this mechanism, how this copper depletion changed the metabolism of cancer cells. And you can read it more the results in this mechanistic study of this system in the recent paper published in Nature Biotechnology. So with that, I want to wrap up this talk. And so we have done first the beta-lactam-based probe design, and by modulating the structure of the lactam to generate specificity. And more importantly, we can further enhance the detection specificity by designing probes that target 2 or more molecular targets. And the second example is that on the proteases in the detection system, and based on a biocompatible reaction, and we can design in a system which allowed us to image across several imaging modalities beyond the optical imaging. And you can also image that with the MRI and then paired in the tomographic imaging modalities. The last example is that nano platform-based imaging sensor system. And the unique properties of nanoparticles has enabled multiplexing and multiple channel and long-term imaging in vivo. And so by combining all those imaging probes for all the different modalities and the different the multi-targets and multi-parameters, and then we can perform this system imaging of the biology. I think that would greatly enable the imaging approach to study biology. And with that, I want to thank the people in the lab and for all the hard work and the many collaborators at Stanford and also outside of Stanford for their contribution and to the work presented here. And finally, thank the funding agency for the financial support. And also I thank you for your attention, and any of you interested in the work, and I would love to talk to you more. And thank you again.
Thank you very much, Jianghong. That was a very nice talk. I think we have time for maybe 2 questions. We have 2 questions in the chat, so I'll read the first. From RM Gamini. I am interested in using donor acceptor type of intrinsically conducting oligomers in bioimaging. These molecules strongly absorb and emit in the near IR region. Therefore, the molecules can be excited using NIR. If 2-photon microscopy is used, then molecules can be tuned to absorb the near-infrared region and emit in the visible region, allowing utilization of NIR radiation with deeper penetration for excitation imaging by the colors generated from the visible emission. I'm wondering whether you are working on this area.
Yeah, so indeed, that's a great capability and to extend to the near infrared region there. And we started work a little bit in this area. And so the problem is that, with the long the conjugation, and you have to generate a new infrared emission. And so the quantum yield usually is quite low on that, and the brightness could be a potential issue still. And so we are currently trying to work with polymer chemists and then trying to address that problem on that. So it's great in the direction, and I know that many other labs and also trying to work along that direction on that. And for the fluorescence side, that's one application. But on the other hand, we also look at absorptions of the near infrared region. So we apply that one for the photoacoustic imaging. So one of the example I mentioned that in the last, there's an example for the couple sensing nanoparticles, and that polymers had the near infrared the longer absorption up to the 1200, and that's another opportunity to work with those in the semiconducting polymers for imaging application. I hope I that answer this question.
Thank you. And the last question comes from Nikolai. Many thanks for the magnificent talk. Do you know if any of the presented methods can be used or adapted for neuronal activation imaging? And if yes, how?
Yes, so we are cancer imaging lab, so we don't do much of the neural imaging there. And so the nanoparticle-based system, I would imagine that if you did brain imaging there, and the big problem is that the penetration blood-brain barrier. And so on the other hand, if you do there's imaging at the other tissue locations there, and that probably is just doable on that. And for the self-assembled system there, and I think that is very doable there, because that's starting with the small molecules first, and then penetrating into the cells and assemble the inside on that. That would be accessible to the neuronal the imaging. And so, but we haven't done those experiments, and we mostly focus on the cancer imaging and the bacterial imaging as well.
Thank you.
And yeah, I noticed that. So great. And then yeah, talk to me that. So you're making those polymers near infrared polymer. That'd be great. We can test that in our system there. Yeah, I would love to contact with you to test that ability.
Fantastic. Well, join me again in thanking our speakers, Leticia, Ryan, and Jianghong. And we'll move into the Meet the Editor session. So if you have any questions for our advisory editors or myself or Frank Maass about the editorial processes or their experiences as editors, please enter them into the Q&A chat. We'll take it from there. I'm not seeing any questions immediately. So I'll start with a rather general question that would be directed to our advisory editors. In your role as advisory editor, upon accepting the role, what motivated you to join Angewandte Chemie as an advisory editor? And
who wants to talk first?
Anyone's welcome to go ahead.
Okay, so maybe I just start. Well, I think is a great honor and a lot of responsibility to be part of such a board, but I think it's a great opportunity to shape things And me as a theoretician, I always saw Angewandte as a journal, like primary. Okay, when you learn German, then it says applied chemistry. So I thought that maybe theory is not like the prime target for Angewandte. Of course, this was a misconception, but I see myself like very proud to represent the theoretical community and then just make Angewandte grow also in this direction. So I think it's a great role, and I hope that we can shape things also for the theory community, which is really willing to contribute with the exciting science in Angewandte Chemie.
Indeed. Thank you. Jianghong or Ryan, if you wish to step in or answer.
Yeah, so for my part, I mean, I did give that quite some thought. Well, what we could do, at this position. I mean, I kind of reflect back at the time I started my own career, and I really appreciate that, at that time, and when we send some of our work to other journals, and with the imaging of the mice, and then like in the chemistry journals, they say, well, this not suitable, for the publication in the chemistry journals. But then, Angewandte, took our work and get published there. So in my mind is that, so, I always thought that Angew, is more forward-looking in the journals and look at those futures, the fields and the development in the chemical research on that. And so I feel like, I can come in to share, some perspective in that, the regard. So I'm working, in the interface between chemistry and then biology and even medicine there. And so, and also, my own background. So I worked trained in China and then came to the US there. So I can probably offer a different perspective, and being of the advisory editor there. So with that, I thought yes, and then I'm happy to join, this group of the excellent scientists and to offer some, the hopefully useful suggestions in the future in that regard.
Thank you, Jian. Indeed.
Also, to echo Jianhong's thoughts, I kind of reflected over, what I've seen change during the course of my own career from being a undergraduate to graduate student, and now in the modern era, especially in the light of the internet age and how that's changed how information is sent, how newspapers operate, and how scientific journals operate. I just thought it was a great opportunity, with Angewandte trying to make forward-looking changes in how the journal was run, being part of that, really at the cusp of this change between the older print era and now the largely digital era. And I'm just excited to see the changes that'll come.
We are too, and we're glad to have all of you on board, certainly. So you've had a chance now to, be in the role of an editor. You're also authors and reviewers yourself. Would you have comments potentially on the peer review process, or advice to those who are potentially just starting their career and entering as authors and reviewers? The value of the peer review process as you see it, and what you think where its value lies, perhaps?
Yeah, absolutely. If you don't mind me going for it, because I was thinking about this recently, actually, in light of a few papers that we have coming in the pipeline. And as much as I try to be a perfectionist, no paper we publish is perfect. I think we all know, you sometimes look at a paper that you've published and you cringe when you see a mistake that's made in the final version. That happens sometimes. And so the first and most superficial aspect of peer review is just catching these errors before they make it to print, for the sake of both the authors and also the journal. But also, I've reviewed several papers where the main conclusions were wrong. And I would hate to be in the position where we drew the wrong conclusion about our own science and had that either have to be retracted or have to be corrected, by another group of scientists. So I would urge all people who are reviewing papers to really put in a significant amount of work to the review process. I know that largely depends on the culture that you grow up in and the training that you have, but there's almost nothing worse than a superficial review. I'd rather have an in-depth negative review that challenges our ideas in the paper than a superficial positive review that really didn't give it a deep read. So I would encourage everyone to do a very careful job in peer review.
There is great value for constructive criticism, certainly.
So can I add a comment to what Ryan just said? So I got a lot of requests to review manuscripts, and many of them ask to finish the review in 7 days or 10 days. And I think that presents a significant challenge to many reviewers. I understand that journalists want to, the review process really fast and get a paper, the editorial decision made fast. But, the short time frame usually, make it harder for really in-depth review, of the manuscript. And that's I think probably that's what the problem. Sometimes you see that more like a superficial reviews because people just don't have time, to review, spend much time, and in such short time frame in a window. So I don't know. I mean, is that something Angu really want expect the reviewer to do, and then the fast turnaround time, or willing to give the reviewers a little bit more time to spend, there's a time to critically review the work and improve the manuscript quality.
But perhaps something just really quickly in the last minute. As PIs, you're faced with balancing being an author, being a reviewer, being an editor, being a caregiver, as Ryan brought up. What advice would you have to some of our younger members in the audience who are approaching their careers in academia and the balance and trying to fit that all in? What would be the key bits of advice you would have for them?
I just wanted to mention, regarding this review process, and probably also fits to your question, that I think it's very important to learn to make these reviews for different papers. So I just said, I would like to animate young people really to accept and to promote themselves, if they are not known, to say, hey, I would like to make reviews, because you can learn a lot by reading these papers. I mean, all of us start as an authors, and then eventually you grow, but you are kind of afraid. You think, well, this is not for me to make these reviews, but it is for all of us, right? It's not only a give and take, it's really a process. You learn to make better papers when you also read sometimes these reviews. I mean, of course, sometimes we are all sometimes frustrated because somebody has not understood our paper. But then I always think, well, maybe I didn't explain it correctly. And then this is again a process that you can go through. But the young people, I mean, if they have opportunities to play these different roles, this means to look at science from different angles. And I would like to encourage them to seize any opportunity to play these roles, to start practicing. The earlier, the better.
Thank you.
Yeah, that's great. I had similar thoughts, but I don't think I could say it any better than Leticia. Actually, that was very well said. And I guess my similar thoughts is among balancing all of these things. I think the way I motivate myself to accomplish some of these hard tasks like reviewing papers is to kind of psych myself up by reminding myself that I will learn something. And there's this aspect of continuous education, which is absolutely crucial in any career. And I think reviewing is a great opportunity to learn something new. And as Leticia said, I can't say it any better. Don't be worried that you can't contribute something. You will learn as you read the paper. I will say, to echo what Jianghong and Suzanne said, an important missing aspect in some of the worst reviews that I've received, I guess I've been on the receiving end of, is non-constructive criticism. That is criticism that is either mean-spirited or just not helpful. And of course, I'm sure we've all been in that position before, and internet trolls don't make it any easier to emulate a positive voice. But I think it's really important to edit and re-edit your review so that your criticism is positive and will be received well and actually taken up by the author. The other thing I was going to say is, since with the caregiving came into the equation, is everyone goes through periods that are extremely busy with paper writing, grant writing, peer review, etc. I've found that despite my best intentions, there's no such thing as egalitarian parenting where everyone perfectly balances all the time the load. So just make sure that you discuss with your partner who's going to pick up what chores and responsibilities when, because that'll avoid a lot of strife.
Good scheduling techniques and organization. Well, I'm gonna end it there with our Meet the Editor session. Again, a very big thank you to all three of you for joining us today, and also to our audience for joining us. Leticia, for staying up so late on European time zone. It was a great session, and we'll see you again. Take care.
Yeah, it was fun. Thanks a lot.